few videos, we have discussed the concept of friction. There we have discussed static friction and kinetic friction. And in case of kinetic friction, we have discussed sliding friction only. And thereafter, we solved some examples. Now we are going to discuss about rolling friction, and we will build some qualitative concept about rolling friction. So let's take a situation. Let's take this is a body which has spherical periphery, means it may be a rim, it may be a sphere, or it may be a cylindrical body which is rolling over rolling over a surface. And let's say this is pure rolling, means there is no sliding or skidding. In this case, if we are taking the motion to be pure rolling motion, and if we are taking these two bodies are in their ideal shape, there will be only one point of contact here between these two bodies. And at that point of contact, there will be normal force applied by this surface on this body, rolling body. Okay, so this normal, let me redraw it. There is normal. This normal is perpendicular to the surface. And of course, this normal is against this weight. That is the force uh, due to gravity on this body. Now we can see here, there is no horizontal force on this body. There is no force against its motion. So we can say at this point, there is only one force. You can see it as normal. So we can say that there is no rolling friction. But this is not the situation in practical. Let's take the practical situation and say that there is deformation here. And now these two surfaces are in contact at more than one point actually. What was we were taking in ideal condition that there is only one point of contact. Instead of that, now we are taking the surface in contact. Now let's take a point here on the surface of this rolling body and another point here on the surface of this rolling body. So this point wants to go downward and this point wants to come upward. So this is obvious that the normal at this point by the platform, let's say this is platform on which this body is rolling, normal at this point, let's say n, this n will be greater than the normal at this point, let's say n prime. So n will be greater than this n prime. And then there will be a turning effect this way, which will oppose the rolling motion. And eventually this body will come to rest. Okay, now we are going to discuss the circular motion. So let's say there is a body of mass m moving on circular track. This is the circular track with center O and radius r. Okay, so to keep this body moving on the circular track, there should be a force which is centripetal force, and this force is perpendicular to this velocity and towards the center of this circular track. And we know that centripetal force can be written as mass into centripetal acceleration. We are taking only magnitudes for the sake of convenience because we know the direction. It is towards the center or always perpendicular to this velocity. Okay, we have already calculated this centripetal acceleration as v square by r. In our previous videos, we have calculated it. So centripetal force will be mv square by r. Now, what is the origin of this centripetal force here? Means which force is acting as centripetal force here? Centripetal force we are calling because of its nature that it is always directed towards the center. But there should be some force which is acting as centripetal force, as in case of let's say a stone tied with a string moving in a circular path. There was tension in the string which was acting on this stone as centripetal force. Here the tension was centripetal force. In the same way, there should be some force which is acting as centripetal force here, and that force is nothing but static friction here between the surface of this mass and this circular track. So this centripetal force is nothing but the static friction. And why I'm saying there should not be any confusion that I'm talking about static friction acting as centripetal force while this body is in motion. So why am I not taking kinetic friction? So you have to be very clear about that. Look, this friction here in this direction is resisting an impending motion in this direction, means which is not actually happening, but this body wants to move away from the center, but this force is trying to resist that motion and keep the body on the track. So along radial direction, there is no actual motion of this body, and that's why this friction, which is along radial direction, we are calling static friction. There may be kinetic friction here, kind of sliding friction maybe here, if this block is sliding over the track. But that sliding friction will be tangential, which will be against this velocity. This will be the sliding friction or kinetic friction here. But if the friction is against impending motion, which is not actually happening, this friction is static friction. So I hope it is clear that why for a moving body we are taking centripetal acceleration, centripetal force to be due to static friction. The maximum value of this static friction will give the maximum value of this centripetal force. So let's move to the next slide and see this thing in a different way. Okay, so this is centripetal force, this is normal, this is weight, and if there is no vertical acceleration, this normal equals to weight, which is equals to mg. Now, the maximum static friction will give the maximum centripetal force. So maximum centripetal force, as mass is constant, velocity can be changed. So velocity can be its maximum value, and r is also fixed for a particular circular track. So r equals to maximum friction, which is nothing but mu s into m. And in this case, we can replace this m by m into g. So we have V max square equals to this m, and this m will be cancelled out. Then this will be r times mu s times g, or V max will be under root r mu s g, where mu s is the coefficient of static friction between the surface of this moving body and the surface on which it is moving. So here we are getting the maximum velocity on with which a body can move on a circular track, provided that we have its uh, coefficient of a static friction us and the radius of the circular track r, and of course acceleration due to gravity v. This way we can find out maximum velocity of a body which is taking turn on a circular track. Now, if this track is not flat and it is making some angle with horizontal, okay, here we have the diagram for the body moving on a banked circular track, and let's say this is centripetal force, then there should be center here, and let's say we are taking horizontal view of this circular track. So this is the circular track. Okay, at this point, let's say these forces are acting, and why I'm taking this point here, look, even if we are taking extended bodies in diagrams, but in fact we are considering them to be point masses, and this way we are discussing our entire dynamics here. So this force is nothing but normal force applied by the track on the body, and this is of course weight, which is nothing but mg. And now if this angle is theta, angle of inclination, then this angle will be theta, and of course there is, let's say, a vertical direction here. This angle will be theta, and this angle is also theta. You can check it by yourself. This is simple geometry. You can check it how these all angles are theta. Okay, so Let's draw this line extended here. Now we can resolve these forces as per our need. Let's say this centripetal force Fc. What is Fc here? As in the previous case, we saw that static friction was acting as centripetal force. Here, what is acting as centripetal force? Let's see. So, Fc. First, we can say that there is friction between the surface of the block which is moving and the surface of the platform or the surface of the track. So, a part of this friction, a component of this friction, let's say this static friction is Fs. A component of this static friction is along the centripetal force, means is acting as a part of centripetal force. So what is that? If this is, suppose if this is Fs and this is theta, and we want to know its component along this direction, this will be Fs cos theta. So centripetal force has one thing here, which is Fs cos theta. This S is static friction. Now, from this normal, there is a component of normal which is also contributing to this centripetal force. And that is nothing but, let's say, if this normal is making theta with vertical, so this will be n cos theta, but the component here will be n sin theta. So the centripetal force has contribution from this n sin theta also. So we have centripetal force now, one component from one contribution from the component of static friction and another contribution from the component of normal force here. We can rewrite this centripetal force as mass times velocity square divided by r equals to Fs cos theta plus n sin theta. Let's take this equation to be equation 1. And now, what about this n? So here we have another pair. Here, let me make it more clear to you. Okay, this is vertical component of this normal, which is nothing but, if this is theta, this will be theta only, and this is nothing but n cos theta. And this is friction Fs, and this is theta. There is one component of this friction vertically downward that we can write as Fs sin theta. Because what is happening? This is friction, this angle is theta. Let's say this is Fs, then this should be Fs sin theta. And from here we can see that there is no vertical acceleration. If there is no vertical acceleration, which is the case here, we are not taking this body to be skidding or slipping. We are taking this body to be moving on a horizontal plane. So this n cos theta should be balanced by this mg plus Fs sin theta. So I'm going to write it here. N cos theta equals to Fs sin theta plus mg. This is the second equation. Okay. Now let's say Fs equals to mu s into n for maximum or for its limiting value, so that we can get the maximum value of this velocity. So n cos theta will be equal to mu s into n sin theta plus mg, and then we can transpose this thing this side, then we have n cos theta minus n into mu s sin theta equals to mg, and then we have n into cos theta, taking n common, mu s sin theta equals to mg, or n equals to mg cos theta minus mu s sin theta. Let's take this to be equation third. Now, if we are putting the value of uh, fs and the value of n in the equation first, then what we are going to get m. Now we will be V max as we are putting fs equals to mu s into n by r equals to fs cos theta. Instead of fs, we are putting mu s into n cos theta plus n sin theta, which we are going to now we are going to take this n common, and then we will have mu s cos theta plus sin theta, and then we can put the value of n from here, which will be mg divided by cos theta minus mu s sin theta, and then this term mu s cos theta plus sin theta. Now we can simplify it further. Then we will have V max square equals to m will be cancelled out, r into g, and then we have mu s cos theta plus sin theta divided by cos theta minus mu s sin theta, and we can simplify it further. Then we will have v square max equals to rg, and then mu s cos theta. Okay, we can divide by cos theta, both numerator and denominator containing these trigonometric ratios. So what we can do, we can divide here by cos theta. Then this cos theta will be cancelled out. Here we will get sin theta by cos theta, that will be tan theta. So instead of writing this mu s cos theta, if we are dividing numerator by cos theta, here we are going to get mu s, and here sin theta by cos theta, which is nothing but tan theta, and divided by this one will be 1 only, and minus mu s tan theta if we are dividing denominator by cos theta. So 1 minus mu s tan theta, and this is for V max square. So V max will be nothing but the square root of whole. Okay, this is what. And now I would like to comment one thing here. In the previous case, when the road was flat or the track was flat, where there was no inclination, we can't move on the circular track unless there is friction. Because if there is no friction, if there is mu s 0, then maximum velocity will be 0. But what is happening in this case? Here you can observe that V max can be given as, even if we are taking this thing to be 0, we can say that V max can be, if this thing is 0, Rg, and 0 plus tan theta, that will be tan theta divided by 1 and square root of whole thing. So even if there is no friction, in this case, when the road is inclined, on the track is inclined, even if there is no friction, that is mu s is 0, we can take a circular turn with a maximum velocity up to here, Rg, tan theta, and a square root of all these things. This is all for this video. In next video, we will take some examples to develop our concept of solving the numerical problems.